Alright, so in this video I'm gonna be explaining this important paper with the title Complete the Missing Half, Augmenting Aggregation Filtering with Diversification for Graph Convolutional Networks. This NeurIPS paper in 2022 by McGill and Mila and DeepMind. The core operation of current graph neural network is the aggregation enabled by graph Laplacian or message passing, which filters the neighborhood node information. Though effective for various tasks, in this paper we show that they are potentially a problematic factor underlying all GNN methods for learning on certain datasets, as they force the node representations similar, making the nodes gradually lose their identity and become indistinguishable. We augment the aggregation operation with their dual diversification operators that make the node more distinct and preserve the identity. Such augmentation places the aggregation with a two-channel filtering process that in theory is beneficial for enriching the node representations. In practice, the proposed two-channel filters can be easily patched on existing GNN methods with diverse training strategies, including spectral and spatial methods. So there are different measures of smoothness, like Dirichlet energy. And so the Dirichlet energy of vector x is just a trace of x transpose Lx. Graph signal energy is the signal energy of block x and column vector x defined on undirected graph are separately defined like this and this. So at the level of vector, at the level of block, you can define the energy. And the signal energy represents the amount of contents in a graph signal, and we will draw the correlation between them and explain how they can be used to measure the smoothness and non-smoothness of graph signal. So take a column vector x. X transpose Lx can be written like this. Because of the eigenvector, if you write this, you can write the eigenvector ui and then simplify it to this interesting form, and the frequency lambda I can be considered as a scalar rate. So it focuses on measuring the component of x in direction of non-smooth u sub I, who has a large weight. So a small energy means x does not contain much non-smooth components. Signal x can be decomposed into smooth and non-smooth components, and the amount the non-smooth component, ns is non-smooth, s is smooth. So smooth and non-smooth, if you sum them, it becomes this. So we decouple them. We decompose it into smooth and non-smooth components. And the non-smooth part can be negative. So we define S to measure the smoothness of signal as this. So they did experiments on these datasets, Chamelson, Squirrel, and other datasets. The multiplication of L and X acts as a filtering operation, adjusting the scale of components in the frequency domain. This projection UI transpose X, this one corresponds to large eigenvalue, will be amplified. This corresponds to the one that has large eigenvalue, so it will be amplified, while the one corresponding to the small one will be suppressed. This is an important note in this part of their paper. So these Laplacians can be regarded as high frequency HP filters, and these are low frequency, low LP filters, low pass filters. So on the node level, left multiplying HP and LP filters can be understood as diversification and aggregation operations. So that's why they can design such two-channel learning. And the spectral version is here. So, inspired by these equations, the two-channel spatial-based method can be implemented by designing different aggregator, for example, LP filter, or a diversification operator, which we call HP filter. So these are related forks, and these are the data sets that they used for supervised learning of shallow GNN. They compared their method with graph attention network. They have some improvement. So for HP channel and LP channel, you see different results for sites here. And these are the hyperparameters that they use. For example, their learning rate, their dropout,